Thanks for joining Pioneer Library Systems while our buildings are closed. I'm Clint Gibbons, I'm a high school math teacher, and by now you've seen the diagrams about flattening the curve that tell you how taking precautions can extend the timeline of the COVID-19 spread. And I'd like to tell you a little bit about the math behind that idea. The SIR model was developed in the early 20th century, and it imagines that we can divide a population into three groups: S for susceptible, I for infected, and R for recovered. And over time, the proportion of the population that's in each one of these three buckets is going to be changing. So at the beginning of an outbreak like COVID-19, everyone in the population is susceptible. So this first bucket would be full of the entire population. And over time, some of those people will become infected, and over time, some of those people will move to the recovered bucket and can't be infected anymore. The basis of the SIR model is a system of three differential equations that I'm about to show you. And if that word doesn't mean anything to you, don't worry, I'm going to explain what I mean. All it means is that on the left-hand side here, this expression ds dt is the rate at which the number of susceptible people is changing. di dt is how fast the infected population is changing. dr dt is the rate at which the group of recovered people is changing. Now ds dt is assumed to be proportional to the number of contacts between susceptible and infected individuals. So we write that ds dt equals some proportionality constant, I'll say alpha, times s times I. So it's proportional to both the number of susceptible and infected people. The rate of change of the infected population is actually, there should be a negative sign in front of that because it's going down as the susceptible people become infected. The rate of change of infected people has a term in it that goes up as susceptible changes to infected to match, but it also has a term going down that has to do with just how many infected people there currently are, because over time there's a proportionality constant beta. Some fraction of the currently infected people are recovering. And so the rate of change of the recovering population is just that same proportionality constant times I. Let's use the computer to try to solve this system and see what it shows us. So I've set up a little Excel spreadsheet that numerically solves this system of differential equations. In the first column here, you see time measured in days. In this second column, the percentage of the population that is currently susceptible, the percentage that's infected, and the percentage that's recovered. And right now I haven't set the parameters to meaningful values. They're both 0. But if I change the infectiousness factor to, let's say, 1/2, which means that on average, a patient will infect another person every 2 days. And if we change then the recovery rate to 1/3, which means it takes on average 3 days to recover, then we get a system like this, where you see the susceptible population decreases from 100% down to about 40%, and the recovered population goes up to about 60% over time. And this orange curve here is highlighting what the infected population looks over time. That's that curve that those diagrams want you to flatten. And at the peak of infectiousness, in this particular example, you see about maybe 7% of the population is infected with the disease at once. Now, a number that epidemiologists and public health experts care a lot for a disease is R0, R0, the basic reproduction number. It's the ratio of these two parameters, the infectiousness factor and the recovery rate. And if that number is bigger than 1, like it is here, then your outbreak's going to spread. If it is less than or equal to 1, as I can make it by changing this to 0.5, then even if there's a small number of infected people, the outbreak stays steady. The susceptible number is 100%, no infected people. Let's talk about a more virulent disease, maybe setting this to be 0.35 and the recovery rate to be 0.15, so that R0 is about 2.3, which is within the plausible range of values for the COVID-19 virus. Then you see that there's a very high peak where over 20% of the population is infected at one time for this particular outbreak. So if we want to flatten that curve, then we could take public health measures like vigorous hand washing and social distancing, and maybe the infectiousness factor goes down from 0.35 to 0.25 if we're very effective. And you see that that curve is a lot flatter now, and only as much as 10% of the population is infected at any one moment. And so that's why epidemiologists and public health experts want us to take these measures. It's because the SIR model tells us that reducing the infectiousness of the disease is a good way to flatten the curve. I hope you enjoyed that. For more math in your everyday life, try Things to Make and Do in the Fourth Dimension, a mathematician's journey through narcissistic numbers, optimal dating algorithms, at least 2 different kinds of infinity, and more, by comedian Matt Parker. It's available as an ebook with your library card through Overdrive or the Libby app.